Hi everyone. Let's start today's session. This is the 12th and last session of this course. So in the previous two lectures, we talked about efficiency of programs and algorithms. We looked at several complexity classes of algorithms. Including constant time, log n complexity, linear complexity class. We also looked at quadratic or polynomial complexity and exponential complexity. The last complexity class that we did not discuss yet in detail is the log linear complexity, and that's something that we will discuss in the second part of this lecture today. Mainly, we will be talking about searching and sorting algorithms in this class. Searching, as you know, we saw some examples earlier in the course, is finding one item or a group of items within another larger set of items. This could be an explicit searching mechanism, but it could also be implicit searching. For example, we looked at the searching for the square root of a number using a specific algorithm, which was not a number within a list, but we were searching for that number based on some criteria that it must be as close to the square root of a number that we had received as an input. So when it comes to searching, we looked at several different algorithms. We looked at exhaustive enumeration, which is also called linear search, where we check each element within a list, whether it is the item that we are looking for or not. We looked at bisection search, which is a very efficient way of searching, but the prerequisite for that is that the list that we are searching in should be sorted. And we also looked at an example of an algorithm called Newton-Raphson for searching for a number. Now, so far we have looked at linear search, which is kind of a brute force algorithm, also known as British Museum algorithm. In this kind of search, the list through which we are trying to search for our desired element does not have to be sorted. But for the bisection search method, it has to be sorted because we have to divide and discard a part of our list based on whether the item that we are searching for is greater than or smaller than the number that we are looking for. So we looked at two different implementations of this algorithm in the previous class. Some recap, linear search is simply exhaustive search or linear enumeration. We simply go through the list, checking each item one by one. So here we are receiving a list and an element that we want to search, and we run this loop n number of times, where n is the length of that list. And whenever we find the element using this equality operator or this condition, we say that we have found the element. This Boolean variable will be set as true, and when we come out, we would return the value whether it was found or not. So if at any time it went into this if condition, found would have become true. Otherwise, it would remain false as initialized over here. We could speed up this algorithm by simply returning at this point instead of setting this value. But overall complexity of the algorithm, when we keep in mind that the element might not even exist in this list, is still linear, where we can say it's big O of n, where n is the length of that list. So the time required for searching through an element, keeping in view that we are looking at the worst case scenario, is linear, which is big O of n. Similarly, searching through a sorted list using the same kind of um, exhaustive enumeration method, we again receive the list and the element. We have to go through this for loop at least at most n times, but we are not sure whether the element is present in there or not. This is a slightly enhanced version from the previous one. What we are doing here is, since the list is sorted and we know the element might be present anywhere here, but beyond a certain point, it cannot be present because the rest of the list is either greater than or smaller than the element that we are looking for. So we have enhanced the algorithm a little bit. We are either returning true or false from within the list. True in case it is present, and false in case we have gone beyond a point where we are sure that it would never be present since the list is already sorted. But the overall complexity for this, keeping in view that there would be many scenarios where the element that we are searching for is not present in the list, it would still have to run n number of times, where n is the length of that list. So the complexity for this again is linear. Binary search, on the other hand, has a considerable amount of gain in time complexity when searching for an element. Here, what we are doing is we are dividing our search list by half every time, either discarding this half of that half by looking at the middle element and deciding it could either be this way or it might be present that way, unless this item itself is the element that we are looking for. So this kind of divide and conquer algorithm changes the complexity of the search from n to log n. So for example, if we are searching within a list of 100 elements, for the previous two search algorithms that we looked at, which were based on exhaustive enumeration or linear search of a list. In the worst case scenario, we would have to run our for loop or while loop, whichever way we implement that, for 100 times in the worst case if E is not present. But for bisection search, we would have to at most do seven seven iterations within the algorithm, and then we would know whether it's present or not present. We might do less than seven, but at most it would be seven, which is a considerable gain on complexity time. Now, so this is again just a recap of the implementation. I think we went through this in our last lecture in detail. We have First of all, we are checking whether the list is zero. If not, then we run this or call this bisection search helper, which simply is keeping a track of the pointers of low and high received within it. For the first call, they would be zero for the starting point and length of L minus one, which is the last element's index. And in each iteration, um, in each subsequent call to this recursive function, what we are doing is we are setting the high and low values to be either low as the starting point and mid of the list as the end point, or mid as the starting point and high as the end of the list for subsequent search. So every time we go through this recursive call, we are dividing our set of numbers or elements in half, eventually giving us that gain in time complexity. Now, um, since we are dividing the problem size by half every time, the resulting complexity of this would be log n. And as I mentioned earlier, if we just look at the calculation numbers for a linear search, the worst case for 100 elements is 100 passes or 100 iterations of checking for that. Whereas for log n complexity, that would drop from 100 to about 6 or 7. Now, searching within a sorted list is what we would be focusing on, because we want to identify whether it is reasonable or valuable to sort a list before searching, because we are gaining a considerable amount of time efficiency from changing from linear to bisection search. So we know that linear search within a list has the complexity of big O of n, whereas the binary search within a sorted list has a complexity of log n. So what would be the mathematical equation that would tell us when it would make sense to first sort the list and then search within it using our better algorithm of binary search? So that equation would look like something like this. That sort is let this define the time required to sort an unsorted list, and if we add that to the complexity of binary search, which is big O of log n, whenever that's less than linear time complexity, big O of n, then it would make sense to first sort and then use the binary search on it. If we just rearrange this a little bit, it would tell us that the time required by sort has to be less than n minus log n. But we know that for any kind of sorting algorithms, and we will take a look at few of them in a few minutes, this can never be true. So why would or when would it make sense to first sort a list and then search through it? The reason for that is that we have to look at, or we can look at, the amortized cost of sorting. And that would mean that if we are sorting a list once and then running our search algorithm on it many times, then it would certainly make sense to first sort and then go through the searching algorithm. So the previous equation that we saw, sort again is a constant time required to sort a list, and we are then running our search, binary search, which has big O of log n k times. And so when this sort time plus k times log n is less than big O of n times k, which is the number of times we have to do our searching on that list. For large number of k, if k is significantly large, this constant amount of time required to sort that list would become negligible. So if we have a scenario which is which would represent several real world scenarios, real life scenarios, and that we have a list which is initially unsorted, but it would definitely make sense to first sort it and then use our searching algorithm on it many times. So let's now take a look at sort algorithms, and rest of our class would be all about that. And we want to efficiently sort a list of entries. They could be numbers, but they could also be alphanumeric values or any words. Strings can also be sorted alphabetically, and we can, once they are sorted alphabetically, we can run our binary search or bisection search algorithm on it, because the conditions that we are using would remain the same. So we will take a look at, I think, about three different sorting algorithms. There may be more, but there would be three algorithms that we will review the code for in the rest of this class. The first category or first type of sort is also called monkey sort, and this is not a made-up name. You can search for it. Many other names are bogo sort, stupid sort, or slow sort, because we are not really using any reasonable mechanism for doing this kind of sort. And all we are doing is, suppose you have a deck of cards. You throw them in the air, gather them up, and see whatever you gathered, is it sorted or not? If not, then just repeat that process. So this is not a scientific method for searching. If we try to look at its complexity. The best case scenario would be big O of n, but there is no uppercase, or worst case scenario, we may be doing it infinitely and it might never be sorted. So not a very good sorting mechanism or sorting algorithm. And the next one that we would take a look at is called bubble sort. And within bubble sort, what we do is we compare consecutive pairs of elements within a list. And so for every two elements, we compare them. And depending on whether we are doing ascending sort or descending sort, we would swap their values so that the proper element is on the left. And we keep on doing it for every two consecutive values. And at the end of first pass, our smallest element would be in first position, and then we would start from the second one and do it all over again. So we are going through the list of n elements n times. Let's take a quick look at the algorithm. So initially we are saying that swap is a Boolean variable that would represent whether we have made any swaps or not. Initially it is false, and our external while loop is saying that while not swap, which means if you are not doing any kind of swap, then keep on repeating the rest of the code. And within that, all we are doing is we have another loop that starts from the second element and goes all the way to the end. And we are simply checking whether the previous element is greater than the current element. And if it is, we make the swap. Otherwise, we check it for the next one. So this way we are going through the list two times. We have big O of length of L, or big O of n, complexity of this outer loop, and same complexity for the inner loop, because we are going through all the elements two times. When we calculate the overall complexity, it is big O of n square. Let's take a look at a simple um, uh, animation that would tell you. So suppose this is the list. The heights of these bars represent the numbers. They are written at the bottom as well. If we run bubble sort on them, it's checking in every pass. It is checking every two consecutive elements and moving the smaller one to the left. And if we let it run throughout, you can see here that the beginning part of the list is becoming sorted. This was depending on whichever number of um, iteration this was. So this implementation has been done so that it starts from descending order from the end. So it takes the element, keeps on taking the larger one to the right, and places it at the end where it belongs. So as you can see, this is quite a number of iterations that it has to do. And so the next largest element in every iteration is being bubbled to be placed at its right position. So this is just a graphical representation of bubble sort. And as you can see, this is big O of n square. If the list was 100 elements long, it would have to do a lot of calculations, comparisons, and moving the elements to be completed. So as I said, the complexity for this is n square. Can we do a little bit better than that? Maybe yes. And the next sorting algorithm that we will take a look at is called selection sort. It's slightly different than bubble sort. What we are doing in selection sort is that in every iteration, again, there would be two loops, one running on the whole list and second one doing some operation while looking for a specific element within a whole list. So we are trying to extract the minimum element from within the list and placing it at the first index. And in every subsequent step, we know that first element is now already the smallest one. So we would start from the second one, go all the way to the end, find the next smallest element, place it at the second position. So that way, at any ith step, the first I elements in this list would already be sorted, and all the other elements, we can be sure that they are bigger than the smallest, than they're bigger than the biggest element, or the first I elements, in whichever way we look at them. So here there is a concept of a loop invariant, and the assumption in this is, let's say, there is for every iteration of this sort, there would be a prefix portion and the rest of the portion. And the way we are doing this sorted, we are trying to find the smallest one in this sub list and putting it over here. So by the time we reach here, we would know that all of these elements, first of all, they are all sorted. And secondly, the largest element over here is still smaller than any smallest element present in the rest of the list. So this condition is our loop invariant. We are saying that the list from 0 to I, and the remaining list from I plus 1 up to the end, then in whichever way we divide it during the process of this selection sort, um, the no element from the first prefix, which is this part, is larger than the smallest number present in the rest of the part. And in every iteration, we would take one element from here, put it in here at its right spot, and that way our list will become sorted step by step, one element at a time. So if we take a look at the code, it's quite simple. We have an outer while loop that checks whether our suffix sublist is its length is not equal to length of L, which is the ending point. And within that, we have another loop that is checking for this condition so that we can swap the appropriate elements. If you remember from our first or second lecture, this is a we are using this tuple to swap the two values instead of using 3 or 4 statements. So the outer loop runs length of L times. The inner one starts from one item ahead and runs for n minus 1 times. The overall complexity of selection sort is again n square. Let's take a look at quick look at its implementation or animation. If we do selection sort here, what it's trying to do is, if you take a look at the beginning, at every iteration, it looks for the smallest element and place it at the next index. And as it goes along, any part up to here that it has sorted, we can be sure that no element in this list, rest of the list is smaller than what we have over here. So as we go along these iterations, you can see that it's sorting in ascending order. And as the algorithm progresses, the left part of this list, which is becoming larger every time, is sorted, and at the end we reach the end, and last element would be the largest one, which would be the end of our implementation. But again, the complexity of both these loops is big O of length of L, and the overall complexity would become n square. Now, the last sorting algorithm that we will take a look at is merge sort, which is kind of a divide and conquer implementation of searching, and this is definitely better in time complexity than either the bubble sort, selection sort, or insertion sort. So what we are doing is we are trying to divide our list into smaller sublists, and we will keep on doing this division by dividing it in half every time, and we will keep on doing it until the length of the divided list becomes either 0 or 1, at which time we will start merging them back together. And every merge that we will do for those sub lists will be done in a way so that they are individually sorted, and we will start going back, and it would result in a final sorted list. So here's a quick graphical representation. Let's say this is the initial unsorted list. We will divide it in two unsorted parts just by dividing it in the middle. This may be one element smaller or larger than the other one, depending on whether the total number is even or odd. But we will keep on doing this. And these sublists are still unsorted. We will keep on doing this until we reach a point where the number of elements in each of these sublists is exactly one. At which time we can easily compare these two and put the smaller one in the first position, second one, larger one in the second position, and this we will do for each of these sublists. So we will merge every two elements, and put them back in the previous sorted list. So the recursion brought us all the way down here, where we are dividing our problem set into half every time, reaching a base case where the number of elements in each of these sublists is exactly one. Um, and since the element is one, this sublist, each one of these sublists is sorted, and we start to merge these sorted lists into slightly larger lists. And we keep on doing that, going back, and as each sublist becomes sorted, finally we reach back to the original size, and that list is also sorted. Uh, the way we merge any two lists when they are being merged, each one of them is sorted. So let's say we were somewhere here. Let's consider this as the first sublist, this as the second sublist, and they are both sorted. So the way we would be merging them is take the first element from here and first element from here, compare whether which one is smaller, and put that in the result. Okay, which means one would be taken out from this list and added to the result. And then this list would start with 5. The second one still has 2 as the first element. And when we compare these two, 2 becomes part of the result sublist. And that way we can keep on doing this merge, and eventually we would reach a point where both of these lists, all of these elements and these elements, are merged into one final list, and they are all sorted. And this we would have to do a number of times, depending on how big the original list was and how many sublists we created on the way. So here's half of the implementation. This is the process of merging two sublists. Let's call one of them left and one of them right. They are both individually, if you look at them, they are both sorted. And all we are doing it is running one while loop on that, checking whether the ith element at left and jth element on right is which one of them is smaller. And depending on which one is smaller, we are adding that to the result, either adding it from the left side or adding it from the right side. And whichever side we add it from, we increase the corresponding pointer to +1. We can keep on doing this until at least one of these lists become empty, in which case either this or that will become false. We will come out of the while loop. And if there are any elements left in either of these left or right sublists, they will all be appended to the result. For example, what we did over here, since this became empty, everything over here was added at the end of our result without any further checks. So this is a simple implementation of merging two sublists, and the rest of the code is over here, which is the overall merge sort function receiving a list. All we are checking, so this is a recursive implementation of merge sort that has to have a base case, and our base case is that the length of the list that this merge sort received is either 1 or 0. It's lesser than 2, in which case we will simply return the copy of that list. But if not, then we will try to find a middle, and we will use the merge sort, same merge sort algorithm on the left part, same merge sort algorithm on the right part, and the return from this would be a sorted list, and then we are simply merging them. So if you think about it recursively, all we are doing is this is the base case, and then we are dividing our problem set into two by half every time, and sorting them individually, and then at the end merging. And that merge process we saw over here. Okay. I have a slightly better graphical um, presentation for this as well. I'll go to that in a minute. But before that, let's take a look at the merge sort implementation animation. So here, what it's trying to do is dividing the list and then merging them, sorting them individually and then merging them. So it did the first half in the beginning, and each part of that first half it did separately, and then eventually merged the last two big pieces of the unsorted list as well. So here's another um, way to look at our merge sort algorithm. So we have a list which is 8 characters long. The first step that we will do is divide it into two halves. So we send the first half, do a recursive call on that. The second half we will do a recursive call on that again. But this is still not same as our base case, which is the list size should be exactly 1 or 0. So we have to do the same step again. So this is our first recursion level. This is our second recursion level. We divide 8416 into again two equal parts, dividing them in the middle. 84 goes this way, 16 goes that way, and we do the same over here. Our third recursive calls divides these two element lists into further one element list, which are all our base cases. Okay. Now 8 by itself is sorted. There is no other element to compare it to. 4 is by itself, it's a sorted list, so that becomes our base case, and we will start backtracking and using the merge scenario in our code. So the next step would be that 8 and 4 will be merged together using the merge algorithm that we looked at. 4 will be placed first and 8 would be placed second, and this we will do for each one of these subframes. And the next step, of course, would be to merge this list and this list into a sorted sublist. So 4816 would be merged into 1468, sorted version of the same list as we return from our recursive calls. 0259 is the sorted version of 5920. And the final step in this would be that these two 4 element sublists will be merged into this number, this sequence. So we have done this kind of divide and conquer approach to keep dividing until we reach a sublist of one element, and then keep merging them back into a final version of sorted list of the um, um, whole length. So what we are doing at the first recursion level, we are dividing the list in half. So it becomes n divided by 2 elements in each list. At the second one, we would again divide them by half. So we have n divided by 4 elements in each list. And the time or the operation that we are doing at each recursion level is big O of n, where n is the length of L. But we are also dividing the list in half at every level. So for each recursive call, we are consuming big O of log n, as we saw in the binary or bisection search kind of algorithms. And the overall complexity of this dividing and then merging back. So dividing is big O of log n, while the merging back is big O of n. The overall complexity is n log n, which is log linear. All of the previous sorting algorithms that we saw so far, bubble sort, selection sort, I'm not sure if we also saw insertion sort, but it's similar to selection sort with a slightly different implementation. They all have a complexity of n square, which is greater than n log n. And n log n is a kind of a very efficient running time for a sorting algorithm. And I think where sorting algorithms go, there is no other sorting algorithm better than giving us better than n log n complexity. So just a recap of all the sorting algorithms we just looked at. The first one, BOGO sort or monkey sort, there is no upper bound for this. We could keep on doing this infinitely and might never get sorted. There is no scientific method to that sort of throwing everything in the air and assuming or hoping that it will get sorted by itself. Bubble sort gives us quadratic complexity. Selection sort gives us quadratic complexity. But merge sort is very efficient and gives us log linear complexity. And log linear is the fastest that a sort can ever be. Uh, so this brings us to the end of this course. Just a quick recap from the first few lectures. We started with learning about data structures, how to store different types of data, what kind of structures we have available. There are some scalar data types, some compound data types as well. We talked about lists, tuples, dictionaries. Then we studied about the concept of iteration and recursion as part of our implementation of algorithms. We also went in great detail about decomposition of our code into functions and classes. So the concept of abstraction, hiding of the data, and then organizing and modularizing our code into classes and functions. We went through all of that. And in the last two lectures, a little bit might have been boring, but very valuable. We talked about different classes of algorithms based on their complexity. And we took a look at some very interesting searching and sorting algorithms in detail. Uh, the the key of this course was to turn our minds towards computational thinking. That any problem that we look at in the real world, can we transform that into a computational problem in our mind and then try to solve it? And many times we can come across, no matter which industry we belong to, we might be a mechanical engineer or a civil engineer, but whatever kind of problem that we come across, whether it's a mathematical problem or a logical problem, can we design a program in any programming language of our choice to make the computers do what we want it to do? It might be trying to solve a mathematical problem. It might be something related to a mechanical engineering problem or a civil engineering problem. It might also be related to chemistry or biology. But the concepts that you have developed as part of this course would have enabled you to transform some real world problems into computational problems, and that would be very beneficial as you go along. So, as a computer scientist, what happens is that you start to look at everything a little bit differently. You think about computation wherever there is a step-by-step process that you have to solve, which might not even really be related to programming, but that's how computer scientists start to think. They think about abstractions, they think about algorithms and problem solving, and they think about automation of a long list of steps and how things can be repeated or automated in terms of making them easier to be repeated. And so the three A's of computational thinking: abstraction, which is related to the representation of data, how you store it, define relationship between them, whether to use objects, classes, functions, different data types. How can you represent the set of elements that you have to deal with in a programming language? And then you think about mechanizing your abstraction and finding a way to solve a problem that might not even be related to programming or coding at this point, but you think about making an algorithm as a diagram and try to see if there is some machine or some language that can interpret your algorithm or your design and then convert it into into code. And last step would be making the algorithm and writing the code in the choice of your programming language, and have computers do that lengthy calculation or a difficult solve a difficult problem for you, not only once but many times, since you as we talked about in the concept of automation. And finally, computational thinking is a concept that many software engineers or computer scientists they uh, think that way. So computational thinking means that for any real world problem, what you are looking at it in a very different way. You are thinking of solving that as a problem, but also you want to make sure that you solve it in a very efficient manner with the minimum number of steps required to do it. And are those steps repeatable in a way that it you can write something about it in terms of code, and then let the computer do it for you again and again. And lastly, once you have completely mastered the concept of recursion and have written a few programs that uses recursion, I think it becomes very easy to look at the real world problems in a way that, can I solve this problem, this large problem, by converting into a smaller problem and trying to solve that smaller problem? And if you have a smaller problem, can you further decompose that into an even smaller problem and try to solve it? And that's simply for every kind of recursive algorithm that we looked at. That's exactly what we did. For a large number of n, if we try to find the factorial, all we have to do is find the factorial for one number less than that. And for that, all we have to do is to find the factorial of one number less than that, eventually reaching the number one, factorial of which is one itself, and just backtracking. So that kind of this was a very basic problem, basic example. But when you think recursively, like we just saw in merge sort, that we kept on dividing our lists, and eventually we reached a level where every list has one element, and then we simply started merging them. And merging was easy, that we have to go through each list item by item, two items at a time, just pick the smaller one and then move on to the next step. So thinking recursively is one of the ideas or abilities that computer scientists or software engineers develop over time, which let them solve larger problems by thinking of them as smaller problems, and then backtracking back to the larger solution. I believe this is the end of this course. I hope you have learned few valuable insights into how programmers or computer scientists or software engineers think about problem solving. And the I think the best way to go forward is to try everything in coding. Don't be afraid to just start programming. You might get a few errors in the beginning, but over time, whichever language you are trying to program in, it would become like a second language to you. And practicing, doing more and more programming is the only way to get good at programming. So I hope you have enjoyed this course. All the videos are available. If you ever want to review anything, you can go back and just rerun that lecture. All right. Thank you, everyone. I hope the future holds good things for you. Thanks. Take care. Bye.